Am I audible?
Yeah, we can hear you.
All right, sounds good. Well, yeah, thank you for sticking around till the end. I will be presenting on behalf of my team, which consists of mostly students from India. So I don't think the two of them are here right now. Debjyoti might be here, uh, but I can present on behalf of all of them. It was great listening to all of the presentations. It's really impressive how much students have done in just a month's time. So I'll begin. So I'll be presenting on this idea of electricity-free PCR thermocycler that I described before. Our team, because we are in different places, we were only able to talk and chat weekly and discuss ideas, brainstorm. Some of the ideas were really good, and I'll try to summarize some of those things here. We did a Fred Park analysis, and I also want to include two of my students who did most of the work that I'm going to present in this presentation. So I know we have 10 minutes. I'll keep an eye out for that time limit, but feel free to stop me if I'm running over. The problem statement is the diagnostic landscape that we have has some key limitations. We've seen this again and again. In 2014, we had Ebola, and then we had Zika. There was always like a case where more testing could have been done. And more recently, COVID has really exposed the gaps in our current infectious disease management system. So typically, the journey of a sample is that it needs to go through these instruments. One is a sample preparation step, which requires something like a centrifuge. And then you need to, for the gold standard detection, you need to amplify DNA, which requires this heating and cooling step done in PCR, and then you can do detection. So there are two bottlenecks that I see in this diagnostic workflow. The first one is centrifugation, and like there have been attempts to do it frugally, like this work where they showed that they could do with an egg beater, although not very reliably. But then this, again, everyone knows this paperfuge was one of the pioneering work in low-cost diagnostics and centrifugation. I wanted to put this here because other teams are discussing drones. We harnessed a drone and replaced the motors with these 3D printed cartridges that can do spin column assays without centrifuges. The other bottleneck is this thermocyclers, and again, these require a lot of power and are expensive. So there have been attempts to do this in a like a microfluidic format, and although successful, they still require peripheral components like syringe pumps. So we did this customer discovery last year and even this year, where we're talking to many people who do diagnostics at like rural settings and developed settings. And we asked them questions of what the key problem was during pandemics, and ask them to rate these metrics. So depending on who you ask, you get different answers. So we try to club that together. If you ask developed nations, they want more sensitive tests. But if you ask developing questions, they require instruments that can be cheaper and require less power. And this follows from this fact also that 9% of the global population don't have access to reliable electricity, right? And PCR machines require 100 to anywhere 1,000 watts of electricity to run for 30 minutes, right? So that's not available everywhere. So the motivation was, how can we do this in an electricity-free manner? So before I discuss an idea, I want to try discussing some ideas that we tried, but didn't work as well, because I think it'll be interesting for this class. If you've seen this toy, you know what's happening here. This is a drinking bird. The interesting thing here is there's no batteries and there's no electricity, and this can oscillate like this for hours. And the way it does this is through a cool principle of thermodynamics, which is based on the vapor pressure and the boiling point of certain liquids. So chlorobenzene is inside, and it has near room temperature boiling temperature, and that allows it to go up this capillary tube and then condense and come down. And so this oscillation can go as long as the head part of the bird is kept cool. So we thought of using this idea to do a PCR cycle. So we have like two baths here, hot bath and a cold bath, and a PCR tube dangling on like a wire. And because this oscillation can happen for an hour, the idea was to do this thermocycling. But when we measure the temperature profile, it's not very reliable. The temperatures spikes are not very controllable. And the reason is because the system depends on external parameters like humidity and environmental temperature. So we can't really control that. We wanted, like we tried to make our own system. This is now a new toy that's not there out there, but it's inspired from the drinking bird. It uses two phenomena. One is capillary action, which drives the fluid from from a reservoir at the top to to this drainage container, and this drainage container has another physics, which is siphoning action, right? So if you've seen a greedy cup, that's what happens here. When the liquid reaches a certain level, it drains everything out. So this process can again happen as long as there is sufficient water here. And this is much more tunable than the drinking board because we can now control all the parameters. So I'm not going to go into details of this, but we did simulate the mechanics of this, knowing like you can Newton's law of mechanics, you can integrate this over time and see what kind of behavior you get. But interestingly, you get two sets of oscillations which are both tunable, and you can control the time period that the bird or the toy takes at each section. So like this work is ongoing. I just thought it was interesting. We haven't shown a PCR reaction yet here, but I think this looks promising as well. But the main project of this class that I want to highlight is this idea of Curie pendulum oscillator. And I've shown this before. If you have a ferromagnetic material, you heat it to a certain temperature, it loses its magnetic properties, and then it detaches because the gravity force becomes stronger than magnetic force. And that will again keep on happening as long as you have like a heat source, like a flame. So again, the beauty of this is that you don't need a temperature sensor. Like these metals can be tuned to have a certain set point at which it detaches and attaches again based on the properties of the material, right? And so if we take a material like we build a setup to study this. We choose nickel because it's easily available and has the lowest Curie temperature that we could find, which is around 370 degrees Celsius. And we put a video camera and a thermal camera to record the setup. And again, this is like a video of what's happening here. But yeah, you can see the oscillations, and then we can also see a thermal camera record the temperature profiles. And you do see oscillations, and this is very reliable. Like if you look at the top temperature, it reliably reaches the Curie point with a small standard deviation. And even the bottom temperatures are reliably reaching like a low point with a small standard deviation. So in principle, this system can do thermal oscillations without any electricity. But the temperatures are not right. So we're working on that part right now. There are systems, the parameters of systems you can tune, like the distance of the flame and the mass of the metal and so on, that you can get, you can change to get different behaviors in a very repeatable manner. And so this is a very new work, like, so we're still, this is a proof of concept. The idea now is to develop an alloy of nickel and copper, which is not ferromagnetic. So it should lower the Curie point of the alloy and get it down to 95 degrees Celsius. So this, people have used alloys before to lower the Curie point of temperature. So this, I think, should work, should not be a problem. And then cast it in a way that you can interface with PCR tubes and do these oscillations. And another, like I think was a great insight from Manu last time, is instead of these translation motions of pendulum, we could try to do like a torsional or rotational oscillations so that the system is more predictable and safe, I think. Yeah, so I'll stop there. It was a fun exercise discussing with other team members. They had some great inputs. Devjot, if you're here and you want to share your inputs, now would be a good time. But it was a fun exercise. And if there are any questions, I can answer them.
Perfect in 10 minutes. We have plenty of time to discuss any comments. I mean, I think one thing that I just want to say, Ashish, is it would be fantastic to also use the current oscillator. I don't know, can you hear me?
Yeah, I can barely hear you.
Okay. The comment I was going to make was instead of changing the alloy, uh, thermal management is fairly straightforward. The
Right.
temperature is actually at the point of your magnet, but what we care about is temperature farther away, and having another material joint with it where there is a thermal barrier allows you to set. So from a robustness point of view, I mean, I love the alloy idea itself, but it's kind of
Yeah.
interesting to couple because then you get arbitrary temperature control. It's just
Right.
whatever the thermal barrier or a gating function between the two is. So there is a lot
Yeah.
more tunability in that space.
So using thermal conductivity and thermal properties of the material insulation, yeah, you can get that temperature. Yeah.
Has a thermal barrier, and then there is another material which is where the Eppendorf tube is kept. And so
Yeah.
you have a new gate, and you can choose the rate of flux into it. You can determine all of the. You just have a lot more parameters because we get to decouple the thermal management and the magnetic management.
Yeah. Yeah. That's there. I just want to add one thing that it does take some time for thermal equilibrium to reach. So if you do have a thermal barrier, you might lose those. Like we tried putting like a rubber and putting a thermocouple on top of that rubber, but the oscillations frequency is much faster than the time it takes for the temperatures to equilibrate throughout the material. You know what I mean? So that's a challenge when you're using insulation as a means to control this.
Because then you essentially model the entire oscillator, including the thermal side of the story.
Yeah.
Yeah. Any other comments, questions? Yes. You can repeat it, Kevin.
How strong is the rotational? Like, because it's going to be carrying the tube and with some liquid. I don't know how much that is significant to like.
Yeah, I can barely hear you. You're talking about rotational something.
Yeah. So what was the second part? Like,
Yeah, I'll explain the question. It's basically the same thing we talked about, Ashish.
Yeah.
The question was when a tube is dangling on
Yeah.
a oscillator like that, there will be sloshing and other types of things. So
Correct.
just the stability of that associated. And I think, that was the point around torsional versus traditional pendulums. Maybe you can
Right.
explain the
Right.
idea more.
Yeah. So yeah, that's a valid point. Something that I like we discussed last time, and Manu pointed out that instead of having a pendulum dangling, you could have a like a spring-loaded rotational system, which like if you twist, it wants to come back to its original orientation. And given that you can tune the spring constant, you have one more parameter now. Like you can make the twisting force less required to detach versus more, and it'll be the same oscillatory motion, but instead of like a pendulum like swinging, it'll be like a clock like oscillation. So that in principle I think is a great idea. We just want to like now bring it to reality by maybe we'll there are these like some twisting like umbrellas that like you twist and you close, and it has the same spring mechanism. So we'll see. We'll draw some inspiration from there, but basically 3D print and try these ideas. Does that make sense? Okay, thank you.
Are you online? Is the